Hello, this video is going to be about using symbolic calculations instead of root locus to solve a problem that was done by another instructor. And the instructor had some criteria like rise time or settling time of zero point 0.8 seconds and overshoot of 5%. But I'm going to show how you can use symbolic processing to get a more exact answer. So first I want to start with the plant that the instructor used. And this is how I'm going to assign the values symbolically. So, this should be a 2. Okay, so uh, the gain is going to be 5. And let's assume that this is a velocity system because there's no integrator here. So it's a type 0 system, so that means it's something like a temperature control system or a velocity system. Let's assume it's a velocity system. And in this case, because A is 1 and B is 2, K is going to be 5, so that's going to be equal to 10. And that means we're going to have a gain of 5 millimeters per second for every percent output. And we'll assign some real units to this stuff. Okay, this is our PID controller, and this is the general formula for a closed loop transfer function. If you have something going on in your feedback, you'd have an H in here. But since I'm assuming that we have unity feedback, we don't need the H. So what we need to do is convert this to this, and that looks difficult, but what you need to do is just multiply the top and the bottom by S over, or S plus A times S plus B times S, and that will be here. This will cancel out this and this, so what you end up with is this KAB times this with, and then there's going to be will have no S, this will have an S, this will be S squared, which is what we end up with down here. And down here you just need to expand and collect all the S's. And so what you end up with is this equation, and this is the characteristic equation. This can be done easily with just paper and pencil, but I'm using MathCAD and it will do it for me. So this is my characteristic equation, and this is all the coefficients of S. You see this is K times A, B, Ki here. And then this is for the second or S to the first, S to the second, S to the third. And this is what we want to have for our desired characteristic equation. And what we're going to do is put 3 poles at minus lambda. So expanding it out, we basically have a binomial type distribution. And then what we need to do is associate or match the coefficients like S to the 0 to S to the 0, S to the 1, S to the 1. And that is done here. Got to stop. And this can be pretty much done by inspection. You can just see that Ki is going to be equal to lambda cubed divided by K times A times B. And this is the 10 that you saw at the very top in the numerator. And you can see that coming down here, we have the symbolic equations for all of these. And again, this is going to be 10. This lambda is something that we can choose to place the real poles, the closed loop poles, on the negative real axis. And the bigger we make this, or actually the more negative we make this, the faster we're going to get the response. And that should be a, okay, so let's go on down. There's a more general solution where we can have 3 poles. When you have 3 poles, you're going to have 1 real pole and 2 complex poles. But the problem with this is that now you have to place 3 poles. And in general, if you make 1 pole, like the real pole, more negative, the real part of the complex poles become less negative, and so you end up fighting a losing battle where you really can't increase the gains by that much. Also, if you're doing this for a customer or for a product, the customer has to be able to know where to put 3 poles. It's really easy with this method up here where there's just lambda. In fact, in our product, what we have is a bar, a little slider bar that you just slide up until you get the desired response. And as you slide the little slider bar up, it increases this value of lambda, or actually it makes it more negative. So this is really the way to go. So we're trying to put 3 poles at minus lambda. So this is the original equation again, and this is how I've assigned the values symbolically. So we have k is equal to 5, a is equal to 1, b is equal to 2, and I have lambda equal to 10. So it's pretty easy to calculate these gains. I can just say, lambda cubed, that's going to be 1,000 divided by 10. So that's going to be 100. This is going to be 300 minus 2, which is 298. And then if I divide that by 10, it's 29.8. And this is 30 times minus 3. So this ends up being a 2.7. It's easy to do it by inspection. So I really think this is much better than trying to fiddle around with the root locus. So now we're going to do a simulation, and MathCAD does not have all this built in like MATLAB does, so I have to write my own simulation, but this shows how to set up the matrices. So I have minus a times b, and this is a two-dimensional array. This is minus a plus b. So this is the number. This k times a times b is a 10 in the original denominator or numerator. And then I have to convert the continuous time to discrete array. So this is the discrete array. Um, these are the values if I wanted to use a difference equation. I'm not using a difference equation in this example, so we'll just skip over that. So I want to simulate 1 second. We should be able to get there in 1 second because we're supposed to get there in 0.8 seconds. And you can see that 0.8 seconds, and we have no overshoot. Now, we're not quite there at 0.8. If we want to get there a little bit closer, all we need to do is make lambda just a little bit more negative. So we're going to make lambda, instead of a 10, we're going to make it a 12, and that will shorten the response. So let's just go down here, and you can see that it makes it quite easily. And I can make that any number I want, but in reality, there is a limit to how high you can make it. Another thing that is interesting is that uh, the example that was given only went to a step from 0 to 1, and let's just try making this a 10. So I'd be making an instantaneous change of 0 speed to 10 millimeters per second, and you can see the response, but it still takes the same time. It just has a greater output. And then let's make that bigger yet. Let's see, where are we? Reference. Okay, let's make that bigger yet. Let's make that 100. And this should drive it into saturation, which it does. But you can still see that we get there without overshooting. And that's the advantage of using the symbolic calculations. Also, I am using a little trick. I'm making it so that the proportional term and the derivative term only are affected by the changes in the actual velocity. So this is actual velocity at the current time, the previous time, and the time before that. And what this does is it eliminates all the zeros. If I put the zeros back in, what would happen is it'll overshoot. And I'll show you that down below here. So let's make this a 10 because that's a more reasonable output. So this should be 2% because we're going 5 millimeters per second for every percent. So if we want to do 10 millimeters per second, we should be able to output 2%. Okay, here I'm using a more typical PID, and I'm showing the integrator. And this is my integrator windup or anti-integrator windup. And basically what you end up doing is you make sure that the proportional and derivative term plus the integrator term do not exceed 100. So what you do is you take 100 and then you change the limits of the integrator depending upon how much the proportional and derivative term happen to be. Now, the reason why this response is a little bit slower is because uh, I'm using, I have, this adds one pole with the KP and the KI. There should be two poles, but because I put a 0 here, um, in other words, this is a KD times the change in velocity. K0 is the position or the velocity. This is the change in acceleration, excuse me. Um, so what happens here is that we're not subjecting our system to that derivative kick by assuming that the target uh, acceleration is 0. If I used positions to generate the acceleration, then what would happen is that you'd see that change in position, and that would cause the derivative kick that nobody likes. So this is what happens when we do the solutions with MATLAB. And you can see this is the response with zeros. Now this looks a lot different because it's using the 2 zeros, but you can see the response is quite good. And the thing I don't like about MATLAB solutions and this solution is this shows or it combines the controller and the system into one transfer function, and it doesn't take into account that the controller has limits. And that's why my outputs up above don't look like this. If I take out the zeros, I get a response that looks closer to like that we have up above. And you can see that I don't have the Ki, Kp, and Kd terms in here. And you can see that the error is going to decrease as a function of this e to the minus lambda t. And the same thing up here, except that you've got all these other terms that are causing the overshoot. And you can see these Kp, Kd, Ki, all these terms are creating the overshoot. They're creating the zeros. So let's go on down and look at another method to calculate the PID gains. And this is called Ackermann's method. And you can look this up on the internet. It's well documented. And basically you have to set up a three-dimensional array. This is for the integrator, the proportional gain, and the derivative gain. Again, this is the gain. This is the 10 that you see from up above. I have to, again, convert the continuous time to discrete time arrays. MATLAB will do that for you. Then I have to convert my lambda in the S domain, the continuous domain, to the Z domain. And I calculate this alpha sub C matrix, and then I use it down here to create my Ki, Kp, and Kd. And you can see that these gains from the Ackermann gains are just a little bit less than the gains that I calculated using the continuous time domain method. Now, these gains will approach these gains as the sampling time gets shorter. So what's happening is that the Ackermann method actually converts or takes into account the sampling time of the controller. Now let's do a Bode plot. And you can see that because we have zeros, the gain goes over 1. This is what's causing the overshoot with the zeros. And then if we come down here, there's no overshoot, but the difference is that the bandwidth now is 0.97, and up here it is much higher at 0.66. So what happens is when you have zeros, it extends your bandwidth, but you have to be careful with zeros because they can cause overshoot. They won't always cause overshoot, but they can cause overshoot. And I'll talk about that in just a moment. So without zeros, you can see that there's no overshoot, but there's, the more phase lag and the phase lag, there's 3 poles here. The phase lag is 270, 3 poles times 90, 270. And then let's plot out the closed loop poles and zeros. And you can see the zeros are uh, too close to the origin. If the zeros are closer to the origin than the poles, and there's 3 poles here, then what happens is you're going to see an increase in gain as you scan from the origin to the zero or to the poles. You're going to get to the zeros first, and that's going to increase your gain in your phase leg and cause that bump or hump in the gain that you see in the Bodhi plot. Now, I have another video where I place the closed loop zeros, and if you can place the closed loop zeros right here, it won't cause much or any overshoot. And also because it's not complex, it won't cause any problems like making like a zero or like a notch filter. You can actually place the zeros to create a notch filter if you know how to do it. So this concludes my video. Again, if you have any questions, let me know. And hopefully people will stop using the root locus and start using the symbolic method. I have another video that basically says root locus is useless because, again, the pole placement is much more accurate and much easier to compute. Plus, once you have the symbolic formulas, you don't have to recalculate everything again. You just do some substitution values for the the values for your registers, I mean for your variables, and then you get the gains. Okay, that concludes my video. I hope you enjoyed it. Bye.